It's a pleasure to be here. So I'll talk a little bit about what big data is and some of the challenges and hopefully a lot of examples. So okay, how many of you have watched Minority Report? Okay, enough, right? How many of you have read the Foundation by Asimov? Okay, so the Minority Report talks about this. They don't use big data for do that, but they use something spooky. But they use there's some way to predict the crimes, and then of course it's a story. It gets very complicated. Thing doesn't work out, etc. So that is case about predicting what a single guy would do. Then the Asimov's Foundation, written in 50s, talks about a story. They using mathematical models. They predict the future of the worlds, and again it's a story. Unexpected things happen, etc. But with the big data, we are entering a world where even these scenarios might be possible. They are not possible right now, but might be possible. Okay. When people start talking about big data, they generally bring in use cases like I just explained, which are like sounds very scary and nobody have any idea how it works out. Let me take a very simple example from a different side. So let's say, now historically the marketeers, so people who market, just broadcast, right? So the very common thing people does is they find a lot of emails and spam us everybody with useless crap. So let's say that you are sending mass emails. Let's say you want some certain response rate. So let's say you are sending 1 million emails with $2 cost for each email. I mean, it's not just cost of sending the email, finding the people, buying the list, clean up, keep the system running, everything, right? Now this would mean for cost of $2 million, you would reach about 10,000 people. Rather, yeah, because they responded somehow. Okay. Now, one very good example of a thing you could do with big data is that you could try to identify 250K, 1/4 of that people who likely to have a reaction rate of 6%. We just went from 1% to 6%. Right? You could try to do this with something like looking at the email address, knowing where they live, like simple stuff. Right? So we are talking about going from 1% accuracy into 6% accuracy. Still 94% of the time you are wrong. Right? But still you could see, if you do the math, you could see it's a lot cheaper and you actually reaching a lot more people. Okay, so this is big data. I mean, yes, when we talk about these things, we come up with this very nice example of predicting the future and all this stuff, but this is where it starts. There are some scenarios you could actually do the real advanced stuff, but remember this example because it's a very good example on to get an idea what's going on. Now, if you think about a day in your life, you would realize there are so much decisions you would make without enough information. It's just we are very good at taking decisions that way, right? I mean, okay, you want to buy a car, which one? Okay, which model? I mean, you ask friends, you just look around, you look at that, check how much money you have. End of the day, you make up your mind. There are people who can't make up their mind, then they don't buy it for a few years, etc. We are reasonably okay with working on that setup. But if you think about a day in your life and what you do, there are so much decisions you take without enough information. And most of it, for example, say I'm going to leave. Would it rain today? Will there be traffic? things like that. Now, if you think about that, actually the information needed to make that decision is available somewhere. It just there's nothing that brings together and put everything together and tells you at the right time what's needed. Again, that's big data. Okay, so this is the very high level outline. So the big data is driven by better computers. There are a lot of computers, a lot of bigger systems. That means more data. Driven by Internet of Things. Driven by the cloud, because again there's a lot of computing power around things happening. Driven by what's called Moore's law of data, which means the data roughly doubles once every 2 years. Okay. So the resulting data are complicated because they are volume, there's a lot of it. Because they are velocity, they're coming too fast and you want to react fast. The variety, there's so many types of it, right? There's structured, unstructured, voice, video, you name it, right? And the veracity, last one, there's a lot of missing data, there's uncertainties associated, your sensor values may be wrong, all the kind of complication. So then the goal of big data is to know what happened, to understand why some things are happening and trying to predict, and you try to do, so let me switch to so you do a lot of good things out of it. So I'll come to those in a minute. So let me say one word about IoT, because that's a very, very powerful driver of all these things. Okay, how many of you have heard the word IoT? Okay, so let me tell you. So the IoT stands for Internet of Things. Very simply put, the idea is that you would put sensors everywhere in the world. Today, like morning, I was listening to something. Like somebody has created a pill that when you swallow, it wirelessly keep emitting like how your stomach is doing for certain time of time. A little bit crazy, but the basic idea is that you put sensors everywhere so that you know what's going on at person level, at different levels, and you make decisions out of it. So let me tell you a dream scenario for IoT. So you are sleeping. Now you're in this perfect IoT world. You are sleeping. The way you sleep in, the way you turn around, etc., your bed decides that you are not sleeping soundly. So the bed would go, I'm not really bed, the events generated from the bed, and the system would go and look at your calendar and figure out that, okay, your first meeting starts at 10 a.m. Check the traffic, fine, everything is good. I can let this guy sleep for 1 more hour. So he'll adjust your alarm clock. And when the time to wake you up comes, your shutters wouldn't suddenly, it doesn't go bang and just wake you up. The shutters would slowly open up gradually, allowing a little bit of sunlight bit by bit, getting you up smoothly. Okay, so I mean, we may or may not live to that world, but this is the world IoT is promising. The power of IoT is that it would connect the physical world with the computing world. It will get so much data connected and so much actions goes back. So that's also a very powerful drive of big data. Okay, so what can we do with big data? The reason this is very powerful is that the world we live in is so inefficient. For example, 30% of all food get wasted between the farm and your plate. In US, about 40% of all cooked food is thrown away. So the GE, General Electric, has this initiative called 1% initiative. What they are saying is improve in your system, improve it 1% and see how much change that would happen. In US railroads, 1% saving would means $2 billion a year. In US healthcare, 1% saving would mean $20 billion a year. To give you context, Sri Lankan total export per year is about 9 billion. Okay, you could see how much room there is. It's not 1% we can improve, there's a lot of room, right? So then, and you can of course do things like the saving lives, etc., like better weather predictions, etc. Also, actually most of the high-tech work, for example, if a design of a car or design of a plane, then 90% of the work happen in computers through simulations. They say that the all science is become computer science because 90% of the time you simulate and then you build the thing and then you just test, make sure it works. But you don't like create 1,000 aircrafts and put it to wind tunnels and test it. You do the analysis, you figure out the right design. Yes, you have to test the physical thing, but very few. Okay. Okay, so hopefully I have told you a little bit what is big data is. Also told you why it is important or what's the potential it has. So the big data system would roughly look like this. It's a very, very simple picture. There's a lot of information coming. This information would either directly processed or they would be stored and processed. After this, so these two modes of processing we call real-time processing and batch processing. After, by processing this, you build either decision models or knowledge, right? And these you use to derive 4 things. The hindsight means you want to know what happened. The foresight means you want to know what's happening right now and you want to control the outcome. The insight means you want to explain what is going on. The foresight means you want to tell what will happen. Okay, so we'll come back to those again. Okay, all these are good. If big data was easy, we will be just going and doing it, not talking about it here. There's no point, right? The reason we talk about here is there's a lot of complications. I'll give you a few examples. Let's say you have 1 terabyte hard disk. There's a lot of it. If you want to store a petabyte, you need 1,000 computers. Okay. Let's assume you want to move that data. Even in a 10 gigabit network, okay, this is 10 gigabit network. There are only few of those in the world. There's one called US Research Network which connects few universities. In a 10 gigabit network, it takes 2 hours to copy a 1 terabyte. It takes 83 days to copy a 1 petabyte. Okay, so this is why if you have taken OS course, Professor Enenbaum says never underestimate the bandwidth of a truck full of tapes, because if you want to get few petabytes over to Jaffna, the fastest way, put it to a car and drive it over, right? Seriously, and so on and so forth. The one very interesting side effect of this is the systems that handle big data, they are systems built with many computers. That means they are distributed systems. Then you have all these complications associated with distributed systems, which make your life very hard. Okay. So we talk about what is IoT, what is big data. We talk about a little bit of the reference architecture. At the rest of the time, I would talk about some of the tools we use for big data analysis, and then how to use some of these tools, like kind of problems you would solve. So first let me show you this picture shows different big data technologies and kind of trying to represent when they are useful, right? The two axes are the y-axis is the size of the data or the amount of data you have to handle or you receive, etc. The x-axis is how fast you would need a result. Okay? So the famous technology MapReduce stands here, where it can handle a lot of data, no problem, but it cannot give you results very fast. It generally at least need minutes. This is technology where you store the data somehow, you read them back and process them. Okay? At the other end, there are technologies called real-time analytics, which include complex event processing and stream processing. These are technologies that could respond very, very fast, but they actually work without storing any information in a disk. They work as the information come in, keeping minimum required information in memory and with a lot of advanced algorithms. So they could respond to in milliseconds. Okay, and if you in the stock market world, they have gone up to microseconds. Okay, so then in between there is your databases, index storages, these are normal databases. They could respond within seconds, but they cannot handle very large data sets. But so the NoSQL, etc. can push that more. Then there are technologies which I call interactive processing. Examples are Apache Drill, the BigQuery, etc. These are technologies that let you issue random queries, and they could respond to them very fast. The only trick is you generally need like quite some number of machines. You partition the data across the machines, and when you issue the query, it will run in many machines in parallel, and they'll bring the results together. Finally, there's a technology called in-memory computing. The very famous thing is something called SAP. SAP has this system called HANA. The idea is that you load all the data into memory and process them within memory. So it is expensive, but it could be pretty fast. Okay. So these are different technologies. So I'll go through two of them in bit more detail. The first one is MapReduce. Okay, this is the technology that gave rise to all this big data and for normal people to start processing data. So so this invented by Google. They created it for their own analysis, which they brought out later. The idea is that you write two functions. There are two types of functions called map function and reduce function. The idea is that you go and write those functions. Then there's a framework. You give these two functions to the framework and say, please run it with the data set. So what would happen? What would happen is that framework would go and read your data. In default mode, it will take each line of the data and it will run your map function giving each line as its input. So you would run a lot of map functions for each, same map function again and again for each line. When it is processed, it would generate some key value pairs. Each map function will generate some key value pairs. Then your framework would sort those key value pairs, okay, and then it would call the reduce function once for each key, passing all the values emitted against that key. Okay. Then reduce function can generate another key value pairs, and that's the output. Okay. For example, now using this, if you want to count, if you have a set of files, if you want to count how many times some word was occurred on those files, what you do is you write a map function which given a line for every word it see, it will emit that word and 1. Okay. So what happen is the map function run through all the files, it will generate lot of pairs saying word 1, lot of them. Then this middle stage would sort them. Then for every given word, it would call the reduce with list of ones where for every one time the word occur. Then in reduce you would just count and emit how many counts again that word. Now important thing to understand is, now this all MapReduce does. It's your job to somehow take your problem and massage it and fit it to this pattern. But interestingly, about 90% of all the problems fit within these patterns. They belong to this category called embarrassingly parallel problems. So people were asking, is this enough? But apparently it is enough for a lot of use cases. There are a lot of use cases that you cannot just do with MapReduce, but they belong to that 10%. There's enough majority so that people can do a lot of useful things with MapReduce. However, the MapReduce is actually pretty slow comparatively. There's a new technology called Spark. Okay, it's Apache Spark. This is a MapReduce or rather Hadoop killer. This would replace the motion is on the way. For example, just last week, the Spark set a new record by processing 100 terabytes of data using 200 machines in 23 seconds. The earlier record was done by Hadoop, where they use 2000 machines, and it takes about 3 times the before. So this roughly about 30 times faster. This for sorting, right? So now if you want to just get started, still go and learn MapReduce, because that's the start point. That's very simple. Spark is a bit more complicated, but for serious things, the Spark is replacing MapReduce very fast. Let me give you a very quick example. The way Spark works, the way Spark works is that you can have a very big file, you point to that and say create a variable. It creates you a variable. It doesn't load it to memory, it don't do anything. It just creates a variable. Then you can say that file and say map and give a function. If you read about the functional programming or like Java 8's lambdas, passing lambdas, etc. It's the same thing. You just pass functions. Then that function would apply for every line in that file. You write a code like this, actual execution would happen across multiple machines, partitions, lot of complications, but it will optimize. The very nice thing about this model is that there are two nice things. One thing is this program is much more readable than MapReduce, because here you just tell, here you are saying run that function on every pair, then you say reduce by key means just grouping, the same reduce part of the thing, okay, then you calculate what you want. So this code you can it's much readable than MapReduce. The B is that here, since you are just telling high level what need to be done, the underlying framework can optimize it a lot. For example, if you do something and if let's say you load some data, do some operations, and do another set of operations, the Spark don't have to read everything from memory again, read everything back. Versus MapReduce, every time you process, it has to go back to the disk and come back. That also makes the Spark much faster. Okay. Okay. So this is great. Now I only still talk about these technologies that let you go to a data in a disk and process them. But there are use cases where it is not fast enough, right? So for example, if you take technologies like complex event processing, they could do, for example, 400,000 events per second, right? So to give you a comparison what that means, assume every event, every one thing it does take a second, then it would take 4 days until you actually go past a second. So think like that's this very fast domain, you scale it up each event into a second, then actually 1 second to happen in real world, it takes 4 days. It is like freezing what's happening, it's so fast. So there are technologies that let you do this. So there are two competing technologies, one called stream processing, the famous